Crown ethers are a special type of ether that are basically as a multi-ether. It's an ether with many ether functional groups all in a ring. And we name them according to the number of the number of atoms in the ring and the number of oxygen atoms in the ring. So what you do is you count the number of atoms in the entire ring, and you would find down here there are 18 in the entire ring. And then you count the number of oxygens, and you find there are 6. So we call this 18 crown 6. And these crown ethers all have their oxygens can be oriented towards the inside so as to make a little cavity that has a lot of negative charge in there due to the non-bonding pairs on the electronegative oxygens. So that central cavity of a crown ether has a lot of negative charge, and positive ions like to go and sit down inside them. But these are positive ions have to be able to fit inside this ring perfectly in order to nest in there. And what we find is the size of the ring determines what ion can sit down inside. Go ahead and try to name this crown ether. If I count the atoms on the outside, I would find there's 3, 6, 9, 12, 13, 14, 15, 16. And then if I count the oxygens, there's 4. So the name of this crown ether is 16 crown 4 ether. The specificity of the size of the cavity specifically attracts certain ions. So the 18 crown 6 ether actually pulls pretty much only potassium ions to the inside, since they fit perfectly inside that size container. Because the inside of this crown ether is just the right size for potassium, the potassium loves to sit inside, and when you put something that has a potassium ion as a counter ion in solution with this crown ether, the crown ether gets pulled inside and leaves its counter ion very negative. In fact, potassium salts have a hard time being dissolved in organic solvents because they're not very polar. But if you put a crown ether in the solvent, the crown ether has a great time being dissolved in an organic solvent. But the potassium also likes to sit inside the crown ether. So the potassium sits inside the crown ether and gets pulled up into the solvent, and the negative ion, its counter ion, just has to go with it because it can't be left behind all naked and negative. So it gets pulled up into the organic solvent by the crown ether pulling the potassium up. So it's a really neat way to get things that wouldn't normally be dissolved in an organic solvent to go ahead and be dissolved. Now, thiols and sulfides are the oxygen analogs of, the sulfur analogs of alcohols and sulfides. The thiol group is often called, it's an old-fashioned name, called the mercapto group, and you would sometimes see this in names. Mercapto actually means capture of mercury, and that is because the big soft sulfur atom loves to coordinate with mercury and other heavy metals that like to pull electrons onto themselves when they're positively charged. And because they're big, the atoms are big, and they have a very flexible way to have electrons around them, the sulfur can mush in there on those atoms, and they're very much attracted to each other. To name the thiols, we've already learned a little bit of this, but just to review it, you just say the alkane name and then follow it with thiol. So ethane, thiol, and cyclohexane, thiol. Thiols all smell bad, or pretty much all of them smell bad. For instance, methane thiol and ethane thiol are used to make the alkane gases have a bad odor. They put them in natural gas, propane and butane, so that when there's a leak, you smell it and take action on it. Thiols are also what give skunk spray such a horrible odor. Many of the really bad smelling compounds, the rotten egg type smells, come from thiols. Thiols are acidic. Notice you can deprotonate a thiol with sodium hydroxide and make a thiolate, a sodium thiolates. So thiols are more acidic than water. Thiols are more acidic than alcohols and even more acidic than water. If you look at this reaction, you can see that a thiol is deprotonated by sodium hydroxide to make a sodium thiolate and water. This is what makes thiols such great nucleophiles, because a thiol is not very basic, a thiolate is not very basic, and it's got that big soft atom which makes it a great nucleophile. So they're not very basic and they're a good nucleophile. That makes their SN2 occur very quickly, making the E2 reaction very slow due to the lack of basicity. So when we use sodium thiolate, we get an SN2 reaction rather than an E2 reaction that we would most likely have with an alkoxide. Thiols cannot hydrogen bond, and so they have very limited water solubility. Don't let anyone deceive you, making you think that thiols can hydrogen bond. Now, thiols do have some polarizability because the sulfur is large, and that polarizability can give it the ability to deform and form a dipole that can help it with solubilizing in polar solvents, but not very much. Thiols are very important in biochemistry. There's amino acids that have thiol groups on their side chain, and these thiol groups can form disulfide linkages between the chains in polypeptides or proteins, and this is an important part of their three-dimensional chemistry and being held in place, the three-dimensional chemistry being held intact in a globular protein. Sulfides are like ethers, except there's a sulfur instead of an oxygen in there. We name them very similarly. For instance, right down here, the common name for this compound, if there was an oxygen in there, would be dimethyl ether. But because it has a sulfur in there, we call it dimethyl sulfide. Likewise, over here, this is called methyl phenyl sulfide. Just like with ethers, we put the alkyl groups in alphabetical order. Sulfides can be nucleophiles also, but they don't have a leaving group on them because carbon bonds, oxygen carbon bonds and sulfur carbon bonds and carbon-carbon bonds and nitrogen carbon bonds, those are hard to break. So when a sulfide acts as a nucleophile, what happens is a charge develops on the sulfur and you make a salt. So when dimethyl sulfide reacts with iodomethane, it makes a trimethyl sulfonium iodide. Notice it is a salt, and it does not lose a leaving group. Now we have some you try it problems for you. The first thing I want you to do is try to name this compound. Select the best common name. When you get through with the common name, we're going to find out what the systematic name would be. Okay, the best common name would be to find the groups that are on there. What groups are on here? We have an isopropyl group and we have a butyl group. We put them in alphabetical order, and so they become a butyl isopropyl ether. This also can be named by looking at the alkane, and here is the alkane chain. So what would we call this? We could call this isopropoxy butane, but we would not be able to call it the isopropoxy butane that we have up here. We would have to call it 1-isopropoxy butane to make sure that you know where it's located on the compound. So what is the major product of the following reaction? If I look at this, this is an alkoxide and this is a primary halide. That's the setup for a Williamson ether synthesis. So if I look at this, you can see that this oxygen is going to do an SN2 on this primary carbon, and it's going to give us an ether. Something I want you to notice about this is that the carbon right here in the alkoxide is not part of the reaction. It is the oxygen does an SN2 on this carbon, and this carbon does not get inverted. This carbon is R and remains R in the product. So keep in mind that the reaction is not on this carbon, but on this carbon, and this is where inversion would take place. So let's look at this reaction here. What is the major product of this reaction? So the major product of this reaction of propane thiol with sodium hydroxide on bromocyclohexane, if you look at this, you can see the sodium hydroxide will deprotonate the propane thiol and make it into the thiolate. The thiolate then can do SN2 on this secondary alkyl halide. What's going to be the product? It's going to be a sulfide. That sulfide is going to have the propyl group on it and the cyclohexyl group on it. So what do we name this sulfide here? Well, because cyclohexyl comes before propyl, we would call it cyclohexyl propyl sulfide. Which is the best combination of reactants to prepare phenyl methyl ether by the Williamson ether synthesis? Well, if I look at this, I can cut it here or I can cut it here. Where would I want to put the alkyl halide? Because I need to be able to do an SN2, and an SN2 cannot occur on a benzene ring. We're going to have to put the halide on the methyl group. So what will it have to be? It'll have to be a methyl iodide as the group that gives you this ether. What would be the alkoxide? Well, because this looks like it was phenol, the alkoxide has to be phenoxide. The reagents needed to form this ether are therefore phenoxide and methyl iodide. Which step below is one of the steps in the acidic cleavage of the ether shown below? Okay, when we look at this ether, we can see that it's a secondary ether and a primary ether. So we know, since there's no tertiary there, that it has to go through an SN2 process. Of course, the oxygen will be protonated before any kind of SN2 can occur. All of these have a protonated oxygen except for this one, so this can be eliminated. We see protonated in the oxygens in the remaining three choices. Once it's protonated, what happens? You're going to go to the less hindered carbon and you're going to have nucleophilic displacement. So what are we going to see? We're going to see the nucleophile diving in, taking its electrons and diving into this carbon, because that's where nucleophilic displacement has to go. So here, the iodide is going to the wrong carbon. You can't have nucleophilic displacement there. Here, you have water going into a secondary carbon for displacement. That's not going to occur. Here you have the iodide coming into the primary carbon and the electrons leaving, so this is the correct answer. Which of the ethers below can be prepared by Williamson synthesis? Well, in the Williamson synthesis, you have to have an SN2 reaction. So let's go ahead and look at the oxygens and what they're attached to see if we have a primary carbon that will allow an SN2 to take place without E2 being the mechanism that predominates. This is a secondary carbon, and you would have E2 predominating. This carbon can't even undergo SN2 because it is sp2. Neither of these two carbons can undergo SN2 reactions because they're sp2 carbons. These are tertiary carbons and cannot undergo SN2. And if I look at these two carbons have sp2 carbons, and so they cannot undergo sp2 reactions. However, if I look at this one, this is a primary carbon and this is a primary carbon. So what can I do in order to form this? I could have a halide here and the alkoxide over on this side, and the ring would form by an SN2 reaction. So this is the only compound that could be formed from that. Which of the following is a sulfide? This is a pretty easy question. We can see here, this is a dithiol. This is something called an thioisocyanate. This is something called a disulfide. And this is a thiol. So the only thing that is a sulfide is this compound. Which set of conditions will give the following ether synthesis? Well, because this is a tertiary halide, we cannot use a basic compound. So this is definitely a no-no. What you would get would be the formation of 2-methylpropene. Likewise, this number 4 would give you the same result. If I use diethyl ether and hydrobromic acid, nothing would happen. You would have no change in the reaction. So if I look at these two, their possibilities, this is a tertiary halide, and this would be a savolysis reaction if it made this. Which one would give you the best results? Well, if I have it in water, water would be a competing nucleophile, which would give you the alcohol here. So really the best answer would be to have ethanol and a little bit of heat to stir up the reaction. What is the name of this cyclic ether? Well, if I count up all the carbons, you would find there are 10 carbons and 5 oxygens. The total number of atoms in the ring is 15, and there are 5 oxygens, so it's 15 crown 5.